Hello everybody, welcome to this video series on Surds. The reason that I'm not going through the GCSE paper anymore is because it dawned on me they're no good if you don't actually understand the topics. They don't mean anything. You need to learn the material before we can answer the questions. So in this video and the two subsequent videos that follow, we will be investigating Surds. Now then, what are Surds? The definition that you could write for your GCSE exam or even an A-level exam is that surds are numbers written in the form the square root of n, where n is, and I'm going to do this in a different color, natural and n is not equal to t squared, where t is, and again in blue, natural. So give yourself a moment to just read over and familiarize yourself with this definition. Surds are numbers written in the form square root of n, where n is natural and n not equal to t squared, where t is natural. So as we've written it in a different color twice, why don't we spend some time talking about what natural numbers are? Very difficult thing to get your head around. Okay, are you ready? The natural numbers are as follows: 1, 2, 3, and so on. That's right, I'm only joking. Those are natural numbers. Natural numbers are 1, 2, 3, 4, 5, 551, 552, and so on and so on. 1,225,151, 1,225,000, yada yada, 53. Whole positive numbers. Whole positive numbers. Now you might be wondering, why isn't 0 there? Because 0 being a natural number or not is the oldest debate in the book. Never mind if you are Tory or conservative. Never mind if you prefer McDonald's to KFC. Never mind if you think Chelsea is better than Liverpool, whatever. This is the original argument. Those who are more involved in analysis and the analytical side of mathematics, probability, etc., they will tell you that 0 definitely does not belong in the natural numbers. Whereas algebraists and geometers, they will tell you that 0 definitely does belong in the natural numbers. Ultimately, you are all budding mathematicians, so it is your choice whether you include 0 or not. And you won't get it wrong, whatever you choose. So, this definition looks a little bit hefty. It looks like a lot of unnecessary words. Well, if you think about it, that's not the case. Look at this definition here. T squared, where n is not equal to t squared. Suppose we do have t squared, where the square root of n is equal to the square root of t squared. Well, then this implies that the square root of n will just be equal to t. We don't have positive or negative t. It's just t. I'm going to write this in red so that you remember not to include it. Okay? No. Just positive t. This is important because the square root of t squared is equal to the absolute value of t. Whatever the value of t is, just positive. So by that I mean the square root of the absolute value of minus 9 is just 9. The absolute value of minus 2/3 is 2/3, and so on. So whatever you have for t, could be minus 9, could be 2/3, could be 9. You could have positive numbers. It will not matter. Not one bit. You always take whatever this number is and make it positive. So that's fine if we have, for example, the square root of 4, or the square root of, 9, or the square root of 16, and so on and so forth. These are okay. We can work with these. These are manageable. But what happens if we have the square root of something like 82, or the square root of 15, or the square root of 19? Well, these are no good. These aren't very easy to work with. These aren't very manageable. Thankfully, however, hope is not lost. These are surds. These are all examples, in fact, specifically these three. These are examples of surds. So, in essence, surds are square roots of numbers that aren't whole numbers. Square roots of numbers which, when we take the square root, we don't get whole numbers. So now hopefully this definition is starting to look a little bit more familiar. A little bit less complicated. Now then, you might be thinking two things. You might say, well, if I put, the square root of 82 into my calculator, then I get this number. I get 9.0535385138. Sometimes you might see the ellipses. Sometimes you might see maybe some recurring, but this is what is on my calculator. Can I not just leave it like that? Well, the answer, I'm afraid, is no. Why is this? Because we bring up two very important concepts. One, can we approximate? We know that the square root of 82 is basically 9. Can we approximate? And two, can we write the square root of n as a fraction? The answer to both of these questions is no. We can't do either. Why is that? Well, we can't approximate because, in fact, I will do this in red. We can't approximate because if we do approximate, they're not the same. The square root of 81 is approximately equal to 9.055 and so on. If they were equal, then we would have that the square root of 81 minus, let's just subtract this number, 9.055. If they were equal, this would be 0. Okay, the square root of 16 minus 4 is equal to 0 because they are the same thing. So we can approximate because they're not the same number. Even if we go down to 10 or 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even if we go to 10 significant figures, it's a very, very good close estimate, but they are not the same. They are different numbers. What about writing the square root of n as a fraction? Again, we can't do that. And why? Because of the ancient Greeks. We can't write, and I'm going to write it like this, the square root of n different to the square root of t squared. Just to really highlight, just to drive home the fact that this is not a squared number. N is not 1 or 4 or 9 or 16 and so on. We can't write this as a fraction because of the ancient Greeks. There should be a capital A there. Because of the ancient Greeks. They proved, this is maths. You can't argue with maths. Maths does not care about feelings, because they proved that if the square root of n is not equal to the square root of some squared number, in other words, if n is different to 1 or 4 or 9 or 16 and so on, 25, 36, etc. If n is different to the square root of t squared, then the square root of n definitely cannot be written as a ratio of two natural numbers, where a and b are, here we go in the blue again, natural. This is significant because consider, for example, the square root of 16. This is 4. I'll switch back to black for the time being. Okay, 4, this is a fraction. It might not seem likely at first, but this is 4 divided by 1. This might seem a little bit stupid, a little bit like, you know, don't teach your granny how to suck eggs, but this is important. Again, we could write 4 as 16 divided by 4, or 100 divided by 25. It goes on. But the point is that whatever happens, we can write these numbers t as a fraction, so long as t is a squared number. So as long as t is equal to 4 or 5 or 6. In other words, so long as the square root of n is equal to the square root of 1, the square root of 2, oh no, that's not right, the square root of 4, the square root of 9, the square root of 16, and so on and so on. These are the only instances that will give us a rational number, a number that can be written as a ratio of natural numbers, as a ratio of positive whole numbers. Otherwise, we have an irrational number. Otherwise, we will never be able to write this as a fraction. And again, don't blame me, don't shoot the messenger, blame the ancient Greeks. Okay? So, those are our motivating factors. Those are why we need surds. When we leave a surd in this form, when we leave a number in this form, this is defined. This is okay. This is a number. It's the same with, for example, pi. You can leave pi as pi. If you try and write it out as a decimal, you will have to eventually stop writing. You will have to terminate the decimal. And then you have, as I've written here, they're different. They are not the same. You have to stop writing. So always just leave it in this form. Leave it like this. That's okay. This is defined. We know what this is. Do not write it out as a fraction and mess it up. Now then, that just about concludes why we need surds. In the next video, we're going to go over the surd rules, how we can apply our knowledge of surds to solve problems, and then in the video following, we'll solve some problems. Thank you very much for watching.